Okay. We're going to start with electromotive force, and this is quite possibly the most terribly named concept in all of science. Here's how they came up with the name of electromotive force. They put I think it was zinc and copper is where they started, but they created a layer of zinc right there, and then right on top of it, they put in some conducting gunk. Okay, not non-conducting gunk, but conducting gunk. What? Because non-conducting gunk is what you put into the capacitor. Conducting gunk is different. So just whatever. It's some sort of conductor that goes in between them. And then they topped that with another metal. We'll call that copper. Okay, then more gunk. All right, and then they alternated back to the first one. So now we're back to zinc again, and more gunk. Yeah. Okay, and then more of the first one, or more of the second one, right? Okay. So, and this is what they call a pile. This was the first battery, essentially. And there is, because the valence electrons, one of the metals holds on to valence electrons a little bit more than the other one, then that creates a potential difference here. And this goes beyond the scope of this class. If you really want to get into this, that's why you're taking AP Chemistry, or you've already taken AP Chemistry to get into this stuff. So, I don't know it. That's the other reason why I'm not teaching it. But what they did with this, is, well, illegal by today's standards and twisted in and of its own right. They took wires out of it and they attached it. No, but you're close. No.
Themselves. Cat hat.
I'm gonna go with a mouse.
Chris body part. Making a blind dead one.
That's me.
Skin.
It is a human organ. It's their stomach.
What is that?
Large.
It says frog.
It's a chicken. Oh, it's a frog. It's a frog's
It's
leg.
a frog. Yeah, it's a frog's leg.
They make some cake.
They cut a frog in half.
Oh, that's disgusting.
Good.
The only good part of frogs is don't tell me like the legs started like moving around.
It looks like human without head.
That was a horrible frog head. Okay.
Oh my god.
The rest of the body. That's close enough.
Does it have nose? Or is it or nostril?
What up to his other arms?
Looks like an
Okay.
alien.
All right. So I never said I wasn't twisted. Also, it's just they were also twisted. Okay. And so, anyways, they hooked it up. They hooked the frog up to the pile, and when they hooked it up, and the instant they touched, the legs would fire out. Okay, the legs would shoot out, and so they postulated that there had to be some sort of force that is running through the wires that is going to cause the motion of the frog. Hence the term electromotive force. Okay, that it was the electricity that moved the frog's legs and caused the force to open the frog's legs. Yeah, kind of sick and twisted stuff. That's why it's called electromotive force. We know today now that it's because of the potential difference between these guys. Okay, but this was also the first time that there was a sustained current, and that's really what happened. Is that the electricity gets in here and it collapses the sodium-potassium channels, fires the muscle. Okay, and
So it wiggles?
essentially causes a spasm. What's that?
So it wiggles like this?
No, it doesn't go in and out. It fires at once. Okay, and then you release, and then it would come back. And in fact, I actually did experiments with this in physiology. Not me, not initiated by me. This is a pretty standard physiology experiment. And you do this repeatedly, and you measure the extent to which the frog can actually extend the leg. And you do it 3 or 4 times, and eventually it's just doing like a little twitch because it can't quite fire out like it used to. Okay, this then be called the EMF, electromotive force, and we still kind of refer to this today. We have abbreviated it to a script E. Okay, so you'll see it referred to as a script E, and this is the voltage of a battery. Okay, of cells with no current. Okay, so it's the voltage of a battery of cells with no current through it.
Wait, so voltage is referred to as...
Okay, so electromotive force. We have taken this name, electromotive force, to become our potential. Okay, it is a voltage that causes... Okay, well, it's actually a current, but in order for this to happen, there has to be something driving the current. That's what this pile is for. Okay, this is an electric cell,
So
and
potential is referred to as force in this one because of the
Okay.
sciences.
I started the lecture saying that it is probably the most poorly named concept in all of science. It's not a force. It is not a force. Not a force. Okay. It drove the current that caused the legs to fire. Not a force. Shun. Not a force. Okay. So no, Ashmeet. It's not a force. I know you're struggling with it. I can hear the grunts and the moans.
I can hear that.
Okay.
Not a force. Electromotive.
I can hear the gears of cognitive dissonance grinding upon each other. All right, here we go. So, here's how we actually use it. So we're going to create a battery here. With a switch. And we have okay, we'll call it RL. Here's a resistor. All right. And this is our E. This is our electromotive force. Now, so this can be like our battery, right? So we have this D cell. Okay, we have this D cell in here, and so here's our switch. Let's close the switch, and when we close the switch, we get a current running through it. We call it current this way, although we really know it's really causing a stream of electrons to move in this direction at a really rather slow pace, right? The electrons themselves move slowly. It is the field that happens instantaneously. But because of Ben Franklin's serendipitous decision to make the other direction positive, we just imagine this, that it's actually a series of positive charges that are going this way through the current.
What is D cell?
A D cell battery is one of the big fat batteries that you put into huge fat flashlights. That's just a D cell battery,
Is that rare that you...
as opposed to like double and triple A's. Okay. You've never seen a D cell battery before?
I've seen it, like the thick core...
No. It's
Is a rectangular prism?
no, it's not. It's a cylindrical prism. Okay. This EMF is the voltage of a battery with no current going through it. But if we hook it up in circuit, it's still made out of conductors, and it's still... Sorry.
Less.
Okay. It's still made out of conductors, and electrons still have to flow through it. And unless it goes through completely clean, okay, with no resistance whatsoever, then inside of the battery there is a resistance in and of itself. Okay, and we call this the internal resistance, and we'll call it little r. All right. So as we go on our voltage walk and we walk around here, okay, we need to remember that our voltage, our total voltage, our total change in voltage equals our current times our equivalent resistance. Right? Ohm's law. Voltage equals current times resistance. Okay. Here, however, so we're going to draw this. We're going to draw a graph, and we're going to rewrite this. Okay, so we're going to redraw this in a slightly different way. So we're going to draw this in a horizontal, like it's a horizontal circuit. And we, oh, sorry, I need to put this little one here. That's going to be our little internal resistance, and we're going to have a larger resistance. Okay, and there's our circuit, right? Okay, now if we are voltage man and we're going across and we're going around the whole thing, he keeps track of all of our voltage drops, and every time he comes across a battery, he gains voltage, and every time he comes across something else, he loses voltage. Yeah, it's a capacitor or resistor. We lose voltage because as he goes all the way around to the same place, he has the same voltage that he began with. The delta V equals 0 when you come around to the same place in a circuit. So we're going to draw a graph here where our high water mark is going to be right here. So as we go through, we're going to start at 0. There we go. And as we travel through our voltage increase, we're going to reach our maximum potential, which is EMF. But once the current starts going and he leaves the battery, the internal resistance of the battery will decrease the voltage just a little bit. Then we stay the same as long as, because conductors really have very little resistance. Okay. Then we get to another, and if this is our last resistor, then this has to have all of our voltage, and it goes down there. So we have a tiny delta V here, and we have another delta V over here. And we know that our electromotive force then, minus delta V1 minus delta V2, has to equal 0. Yeah? Well, according to Ohm's law, though, we plug this back in again, and this is going to equal the current that goes through it times the little resistance, and this one is okay, times this other resistance, and I can't remember what the L is for. It's killing me. Capital L.
Large.
No. No, I no. Not important. It's used as an L in your book. Okay, so really this just becomes our electromotive force minus IR minus IRL equals 0. And so that's pretty much it for electromotive force. But this is going to carry directly over into the next title, which is over here. This is going to be resistors in series and parallel. with perhaps the most accurately named term in all of science and math, parallel. I've always been fascinated with that because of the two L's in there, parallel. We've talked about this. Okay. So we've talked about capacitors before. And in our capacitor, we create this magnetic field. Not magnetic field, sorry, electric field. We're not to magnetic field yet. And with this thing storing, I don't want to use that color. We have a Q stored on this capacitor. That's going to give us two things. We know that the potential difference as we cross our capacitor is going to equal, delta V is going to equal our field times the distance of the capacitor. But because it moves along the field, that we're actually losing potential energy. That the test charge would be increasing speed as it goes across the capacitor. So that would be a decrease in our potential energy. And this is given by also given by our charge per our units of capacitance for that one. Well, and this is what stores the energy. Okay, our capacitors store energy in a circuit. We go from there and we get to our resistor. Instead of what affects the capacitor being the amount of charge, what we're really talking about is the rate at which charge is going through this. So we're looking at dq dt, which really equals I. And through Ohm's law, we know that V equals IR. All right, so what happens if we put these one after the other? Let's draw that over here. We'll call this one R1 and R2. Okay, these are in series because there is but one path that you can take around the circle. You can't choose between them. Therefore, you have to go through both, and they're in series. All right. Well, if we're going to do our voltage walk, we start here. We're going to increase our voltage as we go from here to there. And then we walk around and we get here to R1, and our voltage is going to equal whatever the current is that's going through here times the resistance that's going through that. And so that's for the first one. Then for the second one, we're going to have whatever current is going through R2, and that should get us back to 0 as we do our walk around the circuit. Okay. So we can start manipulating this a little bit. I1 R1, well, wouldn't that just be the voltage that's involved on that? All right, that's the voltage for that resistor, and this is the voltage for that resistor. Yeah? Okay. However, regardless of whichever one of these is most resistant, okay, think of them as like a bottleneck or like a fire hose nozzle. That if one of them is more resistant, it's going to slow down the flow of electrons more than the other one. So the other one is going to be reduced to the flow of, so the less resistor, the less resistance, the current going through the less resistance is going to be dictated to how much current is flowing through it by the more resistive resistor. You follow that? That if it's only allowing so much to go through, if the one that's resisting more only allows so much to go through, then the other one just gets what, the current that's left. Okay, and it could handle more, but it doesn't have to. And what that means is that the current through the entire thing, I, is equal to the current in all three of them. So the total current is equal to the current in either resistor. Well, because of that, if this is I and that's I, we get delta V minus delta V is going to equal I times R1 plus R2, and that's going to equal 0. But this one over here, this delta V, is our current times the equivalent resistance. So this is equivalent resistance, and this is I times R1 plus R2. All right, then we can get rid of the I's, and we find that the equivalent resistance is going to equal R1 plus R2. And if we add more things in series, that's just going to go on. Okay, and so if your resistors in series, if they're in a straight line, you just add them up.
This is basically the opposite of capacitors.
Yes. Okay, which brings us to, in parallel, if we have our battery here again. R1, R2, here's our voltage. Okay, that as we go through any particular loop, what's going to stay the same? If we increase our voltage, we walk along, we come over here. Over here we're going to decrease by the same voltage, right? That what stays the same here okay. For this one, we have an I being constant. Our current is constant as we go through our series resistors. Over here, our voltage is constant as we go through our loops. So let's analyze it this way. Since we know our current, well, hold on, let me go back for that. Yeah, so our total voltage equals delta V2. So our
What's that V1 and V2?
equals. They're all equal to each other. That this voltage going this way is equal to that coming down. Okay. Equals I2 R2. Okay. But I equals delta V over R. So we take all these guys and we get okay, our total voltage, our total current here is going to be equal to then gives us that. But what do we know about delta V, delta V1, and delta V2? They're all equal to each other. So we factor them out, and we are left with 1 over Req. Okay, so our equivalent resistance is equal to 1 over R1 plus 1 over R2, and this also continues out for however many series parallel resistors we have. And this is for resistors in parallel. And that is it for this lecture.